Hello and namaste everyone. Welcome to week 7, in particular lecture 27 of this NPTEL course on stochastic approximation. So in the previous 2 weeks we were looking at the asymptotic convergence of stochastic approximation algorithms. So there was one assumption which we refer to as the stability of the stochastic approximation iterates, which says that almost surely the iterates are bounded. Under this in some sense a non-trivial assumption, we discuss the asymptotic convergence. In the next week we will actually discuss ways to remove this assumption. However, in this intermediate class we will discuss the convergence rates of simple stochastic approximation algorithms, so that you get to understand the effect of the step size on how fast you converge. Okay, so let us do a formal summary. So last week we looked at asymptotic convergence of stochastic approximation methods using what we called as the ODE method. In this week we will look at the convergence rates, which means how fast do you converge, and to keep things simple and to get the key idea out, we will focus on the simple case of linear stochastic approximation. By that I mean stochastic approximation algorithms which can be written in the form xn plus 1 equals xn plus alpha n times b minus a xn plus mn plus 1. That is, your function h has the form b minus ax, and because your h function can be written in this fashion, we will refer to this update rule as linear stochastic approximation, right? And in this class, that is in today's class, we will actually keep things even more simpler. That is, we will focus on this very basic algorithm used for estimating the mean of a random variable x, which we had discussed during the first week. Okay, so let us recall the problem that we had discussed, and let us recall how this algorithm was designed, right. So the problem is that we have some random variable x, okay, and its mean is mu equals expected value of x, right, and we have access to IID samples of this random variable x. In particular, at time step n we have access to this random variable xn plus 1. Is that okay? That is, at time step 0 we have access to the random variable capital X1, at time step 1 we have access to the random variable x2, and so on, right. And we had discussed an algorithm of the following form to estimate the mean of the random variable x, right. And now for the simple algorithm we will discuss how the choice of step size actually affects its convergence rate. Okay, to begin with, we will consider the very natural step size choice of alpha n equals 1 over n plus 1, right. So I say natural because once you substitute this step size choice over here, right, you will see that the update rule has the form xn plus 1 equals xn plus 1 over n plus 1 xn plus 1 minus little xn, and by some rearrangement you can see that this expression actually equals x1 plus dot 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 all the way up till xn plus 1 over n plus 1, right. So you can see that by using some simple inductive argument you can show that little xn plus 1 is actually the sum of all the random variables divided by n plus 1. So basically this expression is the sample mean of all the samples that we have observed so far, right. Now given this setup, one can see that since we are taking the sample average, okay, one can view this update rule with alpha n equals 1 over n as the natural thing to do, right. And one would like to know in this case how fast does the algorithm converge. So what we will do is we will subtract mu from both ends, so that we can write the update rule as xn plus 1 minus mu equals xn minus mu plus 1 over n plus 1. So here observe that we have substituted the value of alpha n plus 1, and in the update rule earlier it was xn plus 1 minus little xn. So what I have done is I have added and subtracted mu from in this expression, and written mu minus little xn first and capital Xn plus 1 minus mu n second, right. So now if you define theta n plus 1 as xn plus 1 minus mu and mn plus 1 as capital Xn plus 1 minus mu, so that we can think of this as the noise, then this update rule can be written as theta n plus 1 equals theta n. So observe that this expression is theta n, 1 over n plus 1 is as is, and this is minus theta n, and the noise term is mn plus 1, right. By some rearrangement one can see that if I combine this theta n's together, the the two terms can be written as 1 minus 1 over n times theta n plus 1 over n plus 1 times mn plus 1, right, and this expression leads to n over n plus 1 times theta n plus 1 over n plus 1 times mn plus 1, right. Now the goal for us is to find the convergence rate of the squared error, and hence we are going to square both sides, right. So recall theta n plus 1 is xn plus 1 minus mu. So the error in some sense discusses how far is our current estimate with the value that we are intending to estimate, which is mu over here, right, and hence theta n plus 1 square is the squared error, right. So since theta n plus 1 equals this expression plus this expression, if I square them up I would end up with n square over n plus 1 the whole square times theta n square plus 1 over n plus 1 the whole square times mn plus 1 square plus twice the cross terms, which is 2 times n over n plus 1 times theta n times 1 over n plus 1 of mn plus 1, which will lead to this n over n plus 1 the whole square times theta n of and the product of theta n and mn plus 1, right. Now it is easy to check that theta n is actually a function of these quantities, that is your initial estimate and the samples that we have observed, that is x1 all the way up till xn. More formally one can show that theta n is measurable with respect to the sigma field that is generated by these quantities, right, and we have presumed that your capital Xn plus 1 is actually independent of capital X1 to capital Xn. This is because we have presumed that we have access to this independent sequence of random variables, and since your theta n is a function of these quantities, one can immediately conclude that capital Xn plus 1 is also independent of theta n. Hence if you take the expectation of this cross term, we would end up with the product of the expectations, and if you recall the definition of mn plus 1, right. So your xn plus 1 is an identically distributed random variable, hence if you take its expectation this will be 0, hence this product of expectations will be 0, right, which follows because your capital xn plus 1's expectation is actually mu, right. So if you take expectation throughout, you can see that this expectation will be there, this expectation will be there, this expectation will be there, however the expectation of the cross term will vanish and we will get 0 in its place. Hence we can see that expected value of theta n plus 1 square is n square over n plus 1 the whole square times expected value of theta n square plus 1 over n plus 1 the whole square times expected mn plus 1 square. So notice that the cross term is no longer there, right, and for simplicity what we will again do is we will presume that expected value of mn plus 1 square, which is expected value of xn plus 1 minus mu the whole square, right, and since xn plus 1 is identically distributed as x, this expression equals this, and we will presume that this quantity which is the variance of x is denoted by sigma square, right. So since your xn's are identically distributed, your expected mn plus 1 square will actually be expected x minus mu the whole square, which is the variance of capital X, and we will let us denote that by sigma square, right. Then this expression will change to expected theta n plus 1 square equals n square over n plus 1 the whole square of expected theta n square plus sigma square over n plus 1 the whole square. Now we claim that this update rule shows that, okay, so there is a typo here, that expected theta n square is actually sigma square over n, right. So let us verify this expression. right. So if I substitute n equals 0 in this relation, one can see that expected theta 1 square, right, because n is 0, this term is 0 over 1 square plus sigma square over 1. So you can see that indeed expected value of theta n square equals sigma square over 1 satisfies this claim over here, right. That is, this claim is true for the case of n equals 1. Now for proving the general claim, we plan to use induction, and hence as an induction hypothesis, let us presume that expected theta n square is sigma square over n. Then from equation 1 we know that expected theta n plus 1 square is n square over n plus 1 the whole square of expected theta n square over sigma square of n plus 1, and this expression by our induction hypothesis is sigma square over n, hence we substitute it over here, and this n and this one of the n's will cancel out here, and we are left with n over n plus 1 the whole square, right, and here we have 1 over n plus 1 the whole square. So if you add them up, this n and this quantity over here will give us a n plus 1, which will cancel off with one of the factors in the denominator, leaving us with sigma square over n plus 1, right. This indeed verifies the claim, because the claim was that expected theta n plus 1 square is sigma square over n plus 1, right. So now if we try to summarize, one can see that expected theta n square is the squared error, and this is sigma square over n, right, which tells us the rate at which the squared error converges, right. So one can see that the squared error converges at the rate of 1 over n, which means when you have n samples, right, the error, at least for this basic algorithm, will at most be sigma square over n, right. So if you want this error to be less than epsilon square, one can see that sigma square over n less than equal to epsilon square implies n should be greater than sigma square over epsilon square, which means that to get an error in your estimate to be less than epsilon square, one would need roughly 1 over epsilon square many samples, right, to get to that error. Like for example, if your epsilon was 10 to the power, let us say 10 to the power minus 1, so that epsilon square is 10 raised to minus 2, right. So roughly around 100 samples or orders of 100 samples you would need to get the error to be less than 10 raised to minus 2. So in that sense one can see or get an estimate of how many samples would you need to get the error to be of order epsilon square in terms of squared error, right. So now one can ask, okay, in this update rule we had used this step size sequence 1 over n plus 1, right. Why did we use that step size sequence? Maybe if you had used a different step size sequence, let us say alpha between 0 and 1, right, perhaps we would have got a better convergence rate. Now observe that this quantity over here, right, compared to 1 over n plus 1, right. So if you compare this step size sequence where your alpha is between 0 and 1, that is strictly less than 1, right, then this step size sequence decays slower, this step size sequence decays faster, which means your step sizes are going to 0 much faster, right. So if you go back to this update rule that we had over here, right. So here if your step size decays to 0 much faster, we can conclude that the value over here is going to be very small, and since this value is going to be very small quickly, right, the difference between xn plus 1 and xn is going to be not very different, like xn plus 1 and xn are not going to be very different if alpha n becomes very small, right, and hence a natural thought would be, what if we choose alpha n's to be maybe not 1 over n plus 1 but maybe something that decays slower, in which case your xn plus 1s will actually be much different compared to xn, right, relative to if you had chosen the step size sequence to be 1 over n plus 1, right. And often in practice we may have computed such estimates by choosing alpha n to be a constant which never decays, right. So one may ask, okay, if we choose step sizes which do not decay that fast, do we get a better convergence rate or not. So that is the question that we are going to start answering. We will partially answer that question in this lecture, and in the next lecture we will completely answer that question, okay. And so that there is no suspense, let me already tell you what we are trying to prove. We are going to show that when the step size sequence is of the form 1 over n plus 1 to the power alpha, then your squared error is of the form sigma square over 2 times 1 over n to the power alpha plus some term which is little o of 1 over n to the power alpha, okay. So this means that this expression decays faster than 1 over n to the power alpha, right. In other words, the term that decays slowly in this expression, or the dominant expression, is actually 1 over n to the power alpha, right. So what this tells us is that if you choose such a step size, then the squared error is actually decaying at a slower rate compared to what had happened when we had chosen the step size sequence 1 over n plus 1. Recall that then the error actually decreased at the rate 1 over n, but here we are saying that the error will actually decay only at the rate of 1 over n to the power alpha, which suggests that choosing this step size is actually bad from the perspective of this convergence rate. Is this okay? So from the perspective of convergence rate, one needs to actually choose a step size of this form, right. So now we are going to derive this result. As I said a few minutes back, we are going to build an intermediate expression in today's class, and we will obtain a bound on this intermediate expression in the next class, right. So let us go back to this derivation, right. We have xn plus 1 is xn plus alpha n times capital Xn plus 1 minus little xn, and keeping that in mind, let us again define theta n to be xn minus mu and capital Mn plus 1 to be capital Xn plus 1 minus mu, right. Then again the update rule that we will have would be theta n plus 1 equals theta n plus alpha n minus theta n plus Mn plus 1. Recall that our update rule was xn plus 1 equals xn plus alpha n, here we had capital Xn plus 1 minus little xn, right. So again by adding and subtracting mu to this expression, one can see that we would have this update rule, and again what we will do is we will collect the common terms over here, so that we end up with 1 minus alpha n times theta n plus alpha n times Mn plus 1. Right. So when we had chosen alpha n equals 1 over n plus 1, this was the expression that led to little n over little n plus 1. However, in in our current derivation, this alpha n does not have that nice form, and hence we will stick to this expression. So let us again square this expression and take expectation. So expected value of theta n plus 1 square is what we have over here. Then the square of this expression is 1 minus alpha n square times expected value of theta n square plus alpha n square expected value of Mn plus 1 square. So we would again have would have ended up with a cross term, but since expected value of Mn plus 1 is 0, that cross term vanishes, right, and hence we only have the square of the first term and the square of the second term, right. And again let us assume that the Mn's have a common second moment. In other words, let us presume that the xn plus 1s are identically distributed, so that this expectation is equal to expected value of capital X minus mu the whole square, and let us say we denote this by sigma square, right. And this expression then can be expressed in the following way, which is that expected value of theta n plus 1 square is 1 minus alpha n square times expected theta n square plus sigma square alpha n square, right. Now again let us do some derivation of some expressions for small values of n, and based on those derivations let us try to come up with a conjecture which we will prove using induction, right. So for n equals 0, right, if you go back over here, if you substitute n equals 0, one can see that expected theta 1 square is 1 minus alpha 0 the whole square times expected theta 0 square plus sigma square alpha 0 square, right. and since your alpha your step size sequence is of the form 1 over n plus 1 to the power alpha, where alpha is some number between 0 and 1. If I substitute n equals 0 here, I hope you agree that alpha 0 is 1, and because alpha 0 is 1, this expression over here becomes 0, and hence I have written 0 over here, and the second expression is actually sigma square, but I want to retain this form so that I can use it in my analysis. So this is sigma square alpha 0 square, and hence this expression is sigma square alpha 0 square, right. Similarly, if I substitute n equals 1 over here, I would end up with 1 minus alpha 1 square expected value of theta 1 square and sigma square alpha 1 square. Okay, so that is precisely what I have written here. This is 1 minus alpha 1 the whole square expected theta 1 square plus sigma square alpha 1 square. Now here I am going to substitute this expression over here, so that we end up with 1 minus alpha 1 the whole square times sigma square alpha 0 square plus sigma square alpha 1 square, right. So keeping this expression and this expression in mind, we conjecture or claim that expected theta n plus 1 square is actually sigma square. So you can observe that the sigma square terms are common, so we can pull it out, right, and one can see that for n equals 2 you had 2 terms, right, and for n equals 1 there was a single term. Accordingly, for n plus 1 we start with 0 to n, so that there are n plus 1 many terms, right, and the conjecture is that the summation is of terms of the form alpha k square times the product of j equals k plus 1 to n 1 minus alpha j the whole square, right. So this is the conjecture, and we are going to verify this conjecture using induction, right. So if I substitute n equals 0, right, this right hand side will be sigma square and this n will be 0 here, so there will be only one term to add. So I will now substitute k equals 0, so that I end up with alpha 0 square, and here I have product from j equals k plus 1 to n, so n is 0, so this is what I have, and j will become 1 to 0 1 minus alpha j square. So whenever you have a product where the lower index is larger than the upper index, we interpret such products as being taking the value 1. Is that okay? Because such products are in some sense technically not possible, hence we will interpret this product as 1, right, and once we interpret this product as 1, we see that this expression is actually sigma 0 alpha square, which is exactly what we had verified here. Okay, so now what we are going to do is we are going to presume that the claim is actually true for some arbitrary value of n, and then check if the expression for n plus 1 follows the pattern that we have indicated, right. Now expected value of theta n plus 1 square from our earlier expression equals 1 minus alpha n square times expected value of theta n square plus alpha n square sigma square. So now what we are going to do is we are going to take this expression and substitute our induction hypothesis, right. So wherever we had this expected theta n square, we replace it by sigma square plus the sum that goes from 0 to n minus 1. This is n minus 1 because we have n here, and similarly here also we have n minus 1 because we have n here, and we have this expression, right, and this alpha n square sigma square we retain as before, right. Now because this 1 minus alpha n square, right, is outside, we can take it inside, and every expression here can now be pre-multiplied by 1 minus alpha n square, so that I can increase the upper index of this product from n minus 1 to n, and hence this whole expression will become sigma square, okay, which is over here, times this summation, which is k equals 0 to n minus 1 times alpha k square, this product, where observe that the upper index has now changed, this, and alpha n square times sigma square. Okay, so there is a typo here, since I have pulled this sigma square out common, there will not be any sigma square, right, and this whole expression again by interpreting the product of starting from a higher index and moving to a lower index as 1, one can see that this 1 over here can be written as product j equals n plus 1, okay, j equals n plus 1 to n of 1 minus alpha j square. So if you interpret this as 1, I can replace it back over here, and one can see that this whole summation can be jointly written as summation k equals 0 to n alpha k square product going from j equals k plus 1 to n 1 minus alpha j square, right. So this finishes the verification of this claim, and this brings us to the end of today's class. In the next class, what we are going to do is we are going to obtain a bound on this expression so that we can conclude this result, in particular show that the convergence rate actually is slower when you choose a slowly decaying step size, right. We actually require a step size of the form 1 over n plus 1, right, to ensure that the convergence rate is indeed the squared error decreases at the rate of 1 over n. This is something that we will prove in the next class. Until then, goodbye and thank you. Bye.